Now we are going to start with the first property of an atomic property, that is the atomic radius. So what is it? It is actually a distance from the center of nuclei to the outermost shell of an atom. As you know that this is an electron, sorry, this is a nucleus and there is a electron cloud all around, right. So it is actually the distance from the center of nucleus to the outermost electron cloud, or you can say that it is a distance from the center of nucleus to the region where probability of finding an electron is maximum. So this is what is an atomic radii. You know that it is very like we encounter many difficulties in knowing the exact atomic radii. The reason being the electron cloud do not have a sharp boundary. As we know that like when we start moving from nucleus to a you can say a long distance, then only the probability of finding the electron is not zero. So that means the electron cloud is not having any sharp boundary. Moreover, it is very difficult to isolate a single atom to know its radius. And moreover, distribution of electrons are actually you can say get disturbed due to presence of neighboring atoms. So like you have an atom, so there is a certain kind of distribution of electron, but when you like when you bring some other atom close to it, the distribution of electrons will get somehow affected. So likewise the radii will get affected. And moreover, the atomic radii changes from one bonded state to another. Like whenever the state of the atom, bonded state of an atom change, the atomic radii also changes. But still we try to find out an approximate atomic radii. So we have basic three kinds of atomic radii depending upon that what kind of an element we are talking about, whether we are talking about metal, non-metal or inert gases. So we have atomic radii as covalent radii which operate in case of non-metals. We have van der Waals radii which operate in case of inert gases or noble gas, and we have a ionic radii which operate in case of metals. So we will be discussing that like though these three of them belong to a single category, that is an atomic radii, but still there is a difference between the radii, right. So we are going to discuss that what actually these radii refer to. So first we have is a covalent radii. As I told you that it occurs in case of non-metals. So what is it? Like I'll just explain you the figure, then we'll come to the definition. You know that whenever a covalent bond is formed, which is mainly formed by the non-metals, it is formed by the overlapping of the orbitals. It is formed by the overlapping of the orbitals like I have shown here. Let's say this is a hydrogen molecule formed by the combination of two hydrogen atoms. So this kind of overlapping occurs. So a covalent radii is, so let's say this is the center of nuclei and this is the center of nuclei of this atom. So covalent radii here refers to that this is an internuclear distance. So 1/2 of the internuclear distance between two bonded atoms of same type in a same molecule. So you can say that covalent radii is 1/2, as you saw that, 1/2 of the internuclear distance of two bonded atoms of a same molecule. So here what we have seen is this internuclear distance is approximately 74 picometer. So obviously if you talk about the atomic radii of a single hydrogen atom, so it is obviously divided by 2 because it is 1/2 of the internuclear distance, and internuclear distance is 74. So it comes out to be 37 picometer. So this is how you can know about the covalent radii. Moving on to the another kind of radii, that is in van der Waals radii, and it operate in case of noble gases. It operate in case of noble gases, that is an inert gas. So what is this van der Waals radii? Suppose this is a molecule and this is a molecule, right? So let's say this is AB and this is also BA like this. So again we'll be comparing two adjacent neighboring atoms here. So let's say these are same atoms and they are same atoms of neighboring molecule. So this is, let's say, is a center of nucleus and this is a center of nuclei. So this is an internuclear distance. So this half refers to van der Waals radii here. So what is it? It is the 1/2 of the internuclear distance between two non-bonded, as you saw that these are non-bonded. This is bonded to this A and this is being bonded to another A. So these two B's are not bonded to each other. So the internuclear distance between them is halved, but they should be of similar atoms of neighboring molecule. So this is what is a van der Waals radii. Moving on to the metallic radii. As according to electron seam model, we know that metal exists, metal or metal ions you can say, exist in a metal lattice in a way that these metal ions, let's say these ions, these are floating in a sea of valence electrons. So this is what is an electron sea model. So according to electron C model, what we see is, we see that metal ions or metals, they are floating in a sea of valence electrons. So here what is a metallic radii? These two ions you can see. So distance between any two adjacent metal ions, let's say that this is two adjacent metal ions. So internuclear distance between these two metal ions is just 1/2, and 1/2 of the internuclear distance between the two metal ions, and they should be adjacent in a lattice. That is a metallic radii, which operate in case of obviously the metals. So this is what is the 3 basic atomic radii, and you know that if you will compare that which is the bigger and which is the smaller, so you will see that van der Waals radii is the biggest one, then we have metallic radii, and the lesser one is the covalent radii. So these radii lie in this order. So why van der Waals radii is bigger? As you can see that there is no space wasted actually. Like if we'll do step by step. Let us compare van der Waals with covalent first. So what you see here is that first of all is that van der Waals is a weak force. Van der Waals is a weak force, and covalent as compared to van der Waals is a strong force. So obviously when it is a weak force, so obviously the distance is going to be more. Second thing is that in the covalent one you have seen that some space is actually wasted in overlapping, but no such kind of overlapping is seen in the van der Waals. So that means van der Waals is more than the covalent. And if you compare metal and covalent now, so second turn is that we need to compare metal and covalent. So you'll see that here the atoms are far apart, so obviously it is going to be bigger, and covalent is going to be smaller because the atoms are slightly close, you can say they have been overlapped or they are closer to each other. So this is how you can arrange that van der Waals radii is the bigger, then we have the second number, on second number there is a metallic radii, and the smallest radii is the covalent radii. So these are what is the, you can say, the basic atomic radii. Now we are going to discuss about that how these radii changes along group or period. So this is all about the basic atomic radii. Now we will be discussing that how they vary along group and period.